What if I told you that one of the most promising places in our solar system to find alien life is not on Mars, but on a small, icy moon called Europa, orbiting Jupiter? What if I told you that beneath its 15-mile thick shell of ice lies a vast, dark ocean, deeper than the Mariana Trench, containing more liquid water than all of Earth's oceans combined? And here's the part almost no one is talking about. Right now, while America is slowing down its space programs, China is moving faster and investing more aggressively than ever before to reach that hidden ocean first. They're launching sophisticated probes, developing ice-penetrating robots, and quietly preparing technologies that could let them drill through Europa's ice crust within the next 15 to 20 years. We spent weeks analyzing China's latest space white papers, tracking their rocket launches, studying NASA's delayed timelines, and speaking with planetary scientists. What we uncovered is far bigger than just science. It's about power, resources, and who will control the next great frontier. Because if there is life on Europa, it changes everything we believe about our place in the universe. And if China gets there first, they won't just study it, they plan to claim access to it. This is the story of the deepest ocean in the solar system and the silent race happening right now to reach it. If you've ever wondered what's really hiding in the darkness of space, stay with me. Hit that like button and subscribe, because what we're about to explore could redefine the 21st century. So, are you ready to dive beneath the ice of Europa? Let's begin. Let's start where any journey to Europa must begin, on the surface. Picture this. You're floating above Jupiter's smallest Galilean moon, about the size of Earth's moon. From up here, Europa looks like a cracked, pale billiard ball suspended in the black void. Its entire surface is covered in a thick shell of water ice. Estimates range from 10 to 30 kilometers deep, depending on who you ask. That ice isn't smooth, it's fractured, chaotic, covered in long reddish-brown streaks called linnea. Scientists call them chaos terrain in ridged plains. Some of those cracks are hundreds of kilometers long and look almost like fresh wounds, as if the moon is constantly stretching and tearing itself apart from the inside. Why? Because Europa is locked in a powerful gravitational dance with Jupiter and its other big moons, Io, Ganymede, and Callisto. Every time Europa orbits Jupiter, the giant planet squeezes and stretches it like dough. That tidal flexing generates enormous heat deep inside the moon, enough heat to keep a global ocean of liquid water from freezing solid. Yes, under all that ice, there is an ocean, possibly 100 kilometers deep, more water than every ocean, lake, and river on Earth put together. But getting to it? That's the nightmare part. The surface temperature averages around minus 170 degrees Celsius. That's cold enough to make liquid nitrogen boil away. Any unprotected human would freeze almost instantly, and any unprotected electronics would become brittle and fail. Radiation from Jupiter's magnetic field bathes the surface constantly, a dose that would kill an unprotected astronaut in days, maybe hours. And yet, this frozen shield is not completely dead. Every now and then, scientists detect faint plumes of water vapor shooting out from cracks near the South Pole. Hubble saw them first in 2012. Later observations, some controversial, some confirmed, suggest these geysers can spray water hundreds of kilometers into space before it falls back as frost or escapes into Jupiter's orbit. If those plumes are real and active, they're carrying tiny samples of the ocean below, salts, organic molecules, maybe even microbes, straight into space for us to sample without ever drilling. That's why Europa is so tantalizing. It might be the easiest place in the solar system to taste extraterrestrial ocean water without going through kilometers of ice. But here's where the story gets urgent. NASA's Europa Clipper mission, finally launched in October 2024 after years of delays and budget fights, will arrive in 2030. It will fly by dozens of times, sniffing those plumes, mapping the ice shell, measuring the magnetic field to confirm the ocean's existence and salinity. It's an incredible spacecraft, but it's not a lander. It won't drill, it won't touch the surface, it won't give us direct samples from below the ice. China, meanwhile, has publicly stated interest in a future Europa mission, possibly including a lander or even an ice-penetrating probe as part of its long-term lunar and deep space roadmap. They're not there yet, but they're building the rockets, the robotics, the cryogenic drilling tech, faster than most people realize. So what happens if China develops a way to melt and drill through that ice shell before anyone else? What if the first human-made object to touch Europa's hidden ocean carries a red flag? That question hangs over everything that comes next. Stay with me, we're just getting to the really deep parts. Ready to go beneath the ice? Let's descend. Now imagine we've left the blinding white surface behind and begun our slow descent into the thick ice shell itself, that frozen barrier standing between the known world and one of the solar system's greatest mysteries. This isn't like diving through Earth's ocean layers where light fades gradually. Here, the transition is abrupt and merciless. Once you're inside the ice, sunlight vanishes almost immediately, replaced by an eternal, suffocating blue-gray twilight that filters through kilometers of compressed water molecules. The temperature hovers just above the freezing point of salty brine, cold enough to preserve anything trapped within for billions of years, yet warm enough, thanks to tidal heating from Jupiter, to prevent the entire shell from turning into one solid, lifeless block. Scientists believe this ice crust is not uniform. In many places, it behaves like a slowly convecting solid, with warmer, more ductile ice rising from below and colder, brittle layers cracking and sinking near the top. That churning motion creates the famous chaos terrain we see from orbit. Jagged ice blocks the size of cities pushed upward, overturned, refrozen in grotesque patterns that look almost organic. Some researchers compare it to the pack ice of the Arctic, only frozen in slow motion over geological time. And running through all of it are those long, linear fractures, the lineae, stained rusty red by what most experts now think are salts and sulfur compounds that have welled up from the ocean beneath, perhaps carried by cryovolcanic activity, or simply squeezed through fissures during periods of intense tidal stress. Every time Europa is tugged hardest by Jupiter's gravity, those cracks can open wider, sometimes allowing pockets of subsurface liquid to rise close to the surface before refreezing. In the most extreme cases, and this is where the excitement really begins, narrow conduits may stay open long enough for plumes of water vapor, ice particles, and dissolved organics to erupt into space. We've already detected evidence of these events, first with Hubble in the early 2010s, and later with more sensitive instruments on ground-based telescopes and during the few close flybys of past missions. The plumes don't shoot out constantly. They seem episodic, tied to the Moon's 3.5-day orbit around Jupiter, which means every few days there may be a brief window when material from the deep ocean literally sprays into the vacuum for anyone positioned to catch it. That possibility has transformed Europa from a distant curiosity into one of the highest priority targets in astrobiology. If we can fly through one of those plumes with the right instruments, as NASA's Europa Clipper is designed to do starting in 2030, we might detect amino acids, complex hydrocarbons, or even the faint chemical signatures of metabolic processes without ever needing to land or drill. It would be like tasting the ocean of another world from thousands of kilometers away. But here's the uncomfortable truth that keeps planetary scientists awake at night. Those same cracks and plumes that offer us a shortcut to discovery are also the weak points that future missions will almost certainly exploit if they want direct access. Drilling through solid ice kilometers thick is one of the hardest engineering challenges humanity has ever attempted, far more difficult than reaching the bottom of the Mariana Trench, yet the basic physics says it's possible. Milk probes, hot water jets, thermal lances, even nuclear-powered cryobots have all been prototyped on Earth in Antarctic ice fields in Greenland. China's space agency has been unusually quiet about its own cryobot and ice penetrator research, but their rapid progress in deep drilling robotics on the Moon and in subglacial Antarctic stations suggests they are not standing still. So while the United States focuses on remote sensing with Clipper, quietly building the case that plumes alone might be enough, other players are thinking much more concretely about getting hardware through the ice and what they might find, claim, or control once they do. What happens when the first machine actually touches that dark, hidden water? We're about to find out why that moment could change more than just science. Ready to cross the threshold? Let's enter the midnight zone beneath the ice. We've crossed the brutal threshold of the ice shell, and now the real darkness begins. A midnight zone that has never seen sunlight in billions of years, sealed away under pressure so immense it would crush most Earth submarines like tin cans. This is Europa's global subsurface ocean, a vast, sunless sea estimated to be between 60 and 150 kilometers deep, kept liquid not by geothermal vents alone, but by the relentless tidal kneading from Jupiter that generates heat throughout the Moon's interior. The water is almost certainly salty, rich in magnesium sulfate, sodium chloride, and other compounds leached from the rocky seafloor below, which lowers its freezing point and allows this ocean to remain fluid despite temperatures hovering just above 0 Celsius at the top and potentially warmer near the bottom. What makes this place so profoundly alien is the complete absence of photosynthesis. No sunlight penetrates even the uppermost layers of the ice, let alone reaches the ocean itself, so there can be no plants, no algae, no familiar food chains built on light. Instead, if life exists here, it must draw energy from chemical disequilibrium, exactly the way deep-sea ecosystems thrive around Earth's hydrothermal vents. Imagine towering black smokers on the seafloor, spewing superheated, mineral-rich water loaded with hydrogen sulfide, methane, and dissolved metals. Those chemicals mix with colder seawater, creating gradients that chemosynthetic microbes can exploit, turning inorganic molecules into organic matter and forming the base of a food web that could include tube worms, shrimp-like crustaceans, microbial mats, and perhaps even larger, slow-moving multicellular organisms adapted to eternal night and crushing pressure. Recent modeling and data from past flybys suggest Europa's seafloor might be even more active than we once thought. The Moon's rocky mantle is likely convecting, possibly with plate-like tectonics on a small scale, which would drive hydrothermal circulation far more efficiently than on a dead world like Mars. That circulation could cycle enormous volumes of seawater through hot rock, dissolving nutrients, concentrating organics, and creating countless potential niches for life. Some researchers even speculate that Europa's ocean may have been habitable longer than Earth's, stable for 4 billion years or more, giving any native biology far more time to evolve complexity than anything we've seen in our own planet's deep biosphere. And here is where the stakes become almost impossibly high. If we ever confirm even simple microbial life in that ocean, through a plume sample, a drilled core, or a robotic submarine, it would instantly become the strongest evidence yet that life is common in the universe, not a freak accident confined to Earth. More importantly for the future, it would raise immediate questions about protection, ownership, and access. Who decides whether we send a probe to scoop water, whether we risk contaminating an alien ecosystem, or whether the chemical resources, Hydrogen, oxygen from water electrolysis, rare metals from vents become strategic assets in the new space race. China has made no secret of its interest in situ exploration of icy moons. Their long-term roadmap includes technologies for autonomous cryobots, nuclear-powered thermal drills, and swarms of small submersibles capable of operating under extreme isolation. While NASA's focus remains on non-invasive remote sensing for the next decade, Chinese institutions have already tested prototypes in Antarctic subglacial lakes and published papers on melt probe designs optimized for Europa-like conditions. The gap in capability is narrowing faster than most Western observers admit. So picture this: the first robot to melt through the ice, slip into the dark water, and send back the first images or chemical readings from Europa's midnight ocean. Whose flag or whose logo will be stamped on that machine? The answer to that question could lock in geopolitical realities for generations. Ready to reach the seafloor? Let's descend to the abyssal depths. We have finally reached the bottom, the abyssal zone of Europa's ocean, where the dark water presses down on a rocky, mineral-rich seafloor that may have been shaped by the same kind of relentless geological activity we see in Earth's deep oceans, only driven not by plate tectonics in the classical sense, but by the moon's tidal flexing and internal convection. Here, at depths that could exceed 100 kilometers below the ice, the pressure is staggering, hundreds of times greater than at Earth's ocean floor. Yet the water remains liquid because of the dissolved salts and the steady supply of heat rising from the interior. The temperature gradient is subtle but crucial. Near the top of the ocean, it hovers just above freezing, while closer to the seafloor, it may climb to several degrees Celsius or higher around localized hotspots, creating pockets where chemistry becomes extraordinarily active. The real drama unfolds at those seafloor features we can only infer from magnetic and gravity data collected during previous flybys. Hydrothermal vents, possibly black smoker style like those along Earth's mid-ocean ridges, or perhaps gentler, diffuse flow systems, more akin to the Lost City field in the Atlantic. Superheated fluid, rich in hydrogen, methane, hydrogen sulfide, and dissolved metals, pours out of cracks in the silicate rock, mixing violently with the cold ambient seawater and triggering a cascade of chemical reactions. On Earth, these reactions power entire ecosystems without a drop of sunlight. Microbes fix carbon using the energy from oxidizing hydrogen or reducing sulfate, forming the base for tube worms, clams, snails, and blind shrimp that cluster around the vents in densities that rival coral reefs. If Europa has analogous systems, the same basic biochemistry could be at work, sustained for billions of years in complete isolation from the surface world above. What makes this possibility so electrifying for astrobiologists is the sheer longevity and stability of such an environment. Europa's ocean may have existed continuously since shortly after the Moon formed, perhaps 4 billion years ago, far longer than most habitable windows on Mars or even early Earth before the Great Oxidation Event. That gives any potential life forms an immense amount of time to diversify, specialize, and perhaps develop multicellular complexity in ways we have never observed elsewhere. Some models even suggest that organic molecules delivered by cometary impacts early in the solar system could have been concentrated and cycled through these vent systems repeatedly, creating a kind of natural chemical reactor perfectly suited for the emergence of life. Yet, for all the scientific allure, the abyssal seafloor is also where the geopolitical implications start to crystallize. Accessing this zone directly would require not just penetrating the ice shell, but deploying a submersible capable of withstanding extreme pressure, navigating in total darkness, sampling vent fluids without contamination, and transmitting data back through kilometers of ice and hundreds of millions of kilometers of space. The engineering is daunting, but prototypes already exist. NASA has funded cryobot and sub-ice rover concepts for years, while China's space and polar research programs have quietly advanced similar technologies through Antarctic field tests and lunar drilling simulations. Their published roadmaps speak of in-situ resource utilization on icy bodies and long-duration robotic exploration, language that echoes their approach to deep-sea mining on Earth. If a mission succeeds in reaching the seafloor vents and confirms active chemistry, or unthinkable but possible biological signatures, the discovery would instantly become one of the most valuable pieces of real estate in the solar system, not just for knowledge, but for potential biotechnology, energy sources, hydrogen and oxygen from water, and strategic positioning in the outer planets. Who arrives first, who samples first, and who sets the protocols for planetary protection could determine whether this hidden world remains a shared scientific treasure or becomes another contested domain. So the question that now looms larger than ever, what if the first robot to touch Europa's seafloor isn't American, European, or even international, but Chinese? That moment would mark more than a scientific milestone. It would redraw the map of who shapes humanity's future beyond Earth. Ready to surface again, but through someone else's eyes? Let's talk about the race on the outside. Now let's surface again. Not through the ice, but back into the sunlight of Earth's orbit and the very real competition unfolding among space agencies, governments, and private players who see Europa not just as a scientific puzzle, but as the next strategic frontier. While we've been imagining what lies beneath the frozen crust, the actual race to reach it is happening right now on launch pads, in clean rooms, and in budget meetings halfway across the planet. And the contrast between the two leading contenders could not be more stark. On one side stands NASA and its Europa Clipper mission, which launched successfully in October 2024 after enduring years of cost overruns, congressional scrutiny, and repeated delays that pushed the arrival at Jupiter from the early 2020s into the next decade. Clipper is a masterpiece of remote exploration, a heavily shielded spacecraft carrying the most capable suite of instruments ever sent to an icy moon. Magnetometers to map the ocean's salinity and depth, spectrometers to sniff for organic molecules in any plumes, radar to peer through the ice shell and search for pockets of liquid water closer to the surface, and high-resolution cameras that will photograph the chaos terrain in unprecedented detail. Over the course of nearly 50 flybys between 2030 and 2034, it will gather enough data to tell us with near certainty whether the ocean is habitable, how thick and fractured the ice really is, and whether those plumes are reliable windows into the deep. Yet for all its brilliance, Clipper has one built-in limitation. It is strictly a flyby orbiter. No lander, no drill, no direct touch. NASA's current roadmap postpones any surface or subsurface mission, a so-called Europa lander concept, to the 2040s at the earliest, and even that remains unfunded and conceptual. On the other side is China's CNSA, which has remained far quieter about specific Europa plans, but whose broader deep space strategy leaves little doubt about their long-term intent. The country's 14th five-year plan and subsequent white papers on space exploration explicitly call for in-situ investigation of icy moons in the outer solar system, including technologies for cryogenic drilling, autonomous navigation under extreme radiation, and long-duration power systems, likely radioisotope or small nuclear reactors, that would be essential for surviving Europa's environment. China has already demonstrated rapid progress in related domains. They landed and operated the Yutu-2 rover on the far side of the Moon, returned samples from the lunar South Pole with Chang'e 6, tested melt prototypes in Antarctic subglacial lakes, and are developing heavy lift rockets capable of sending multi-ton payloads to Jupiter-class distances by the late 2030s. Public statements from senior officials emphasize utilization of extraterrestrial resources and expanding humanity's living space, phrases that echo the language used for deep-sea nodule mining on Earth, a domain where China already leads. The divergence is clear and accelerating. While the United States invests in exquisite but non-invasive science from afar, China appears to be building the hardware and operational experience needed for direct intervention, landing, drilling, sampling, perhaps even establishing a persistent robotic presence. If a plume sampling flyby confirms intriguing chemistry, the pressure to follow up with boots on the ground, or treads on the ice, will become enormous, and the nation that has already mastered the logistics of getting there first will hold an almost insurmountable advantage. So here we stand at a fork in the road. One path leads through careful, incremental discovery protected by international protocols. The other leads through bold, unilateral action that could secure access and potentially set the rules before anyone else arrives. Which path will the solar system's hidden ocean follow? And what happens if the first confirmed sign of extraterrestrial life arrives not in a peer-reviewed paper, but in an encrypted data packet stamped with a red star? Let's pause for a moment and really consider what might actually be down there. Not just in abstract scientific terms, but as something tangible that could reshape our understanding of life, technology, and even power in the coming decades. If Europa's hidden ocean turns out to be lifeless, a sterile chemical soup churning under ice for billions of years, the discovery would still be monumental. It would prove that large bodies of liquid water can persist for eons on worlds far from the sun, dramatically expanding the list of places where habitability is possible across the galaxy. But if even the simplest microbial life is present, perhaps nothing more advanced than Earth's deep-sea vent archaea, the implications explode outward in every direction, from philosophy and religion to biotechnology and international law. Imagine a sample returning faint traces of amino acids arranged in non-random patterns, or lipid-like molecules that self-assemble into protocell membranes, or isotopic ratios in methane that scream biological processing rather than pure geology. Any one of those signatures would be headline news for generations, instantly making Europa the single most important astrobiological target in the solar system. Life that evolved independently in a completely isolated environment would tell us whether the building blocks of biology are universal chemistry, or whether Earth's version is a cosmic fluke. It would force us to rewrite textbooks, rethink the odds of intelligent life elsewhere, and confront the ethical question of whether we have any right to disturb or exploit an alien biosphere, however primitive. Beyond pure science, the practical prizes are almost dizzying. Water is rocket fuel when split into hydrogen and oxygen. Europa's ocean could theoretically supply propellant depots for missions deeper into the outer planets, turning Jupiter's system into a kind of gas station hub for future exploration. The hydrothermal vents, if active, concentrate metals like iron, copper, zinc, and perhaps even rarer elements leached from the rocky core. Resources that, in theory, could one day be mined robotically to support long-term outposts or manufacturing in space. And then there's the biotechnology angle. Any extremophile organisms thriving in high-pressure, high-radiation, chemically rich water would be gold mines for enzymes, proteins, and genetic pathways that could revolutionize medicine, material science, and industrial processes here on Earth. Think radiation-resistant bacteria for cancer therapies, pressure-tolerant proteins for deep-sea or planetary engineering, or novel metabolic pathways for carbon capture. Yet every one of those possibilities comes wrapped in risk and tension. Planetary protection protocols, the strict rules designed to prevent forward contamination of other worlds, would become battlegrounds if a nation or company wanted rapid, direct access. Who decides the threshold for pristine versus exploitable? Who owns the first vial of alien seawater? International space law, as it stands today under the Outer Space Treaty, declares that no nation can claim sovereignty over celestial bodies, but it says far less about resource utilization or private enterprise in subsurface oceans. China's track record on Earth, leading in deep-sea nodule mining claims and pushing aggressive lunar South Pole base plans, suggests they may interpret those ambiguities more expansively than Western partners, especially if they arrive with hardware already proven in analogous Antarctic or lunar environments. So the real prize isn't just knowledge or raw materials, it's precedence, the ability to be the first to touch, sample, understand, and perhaps define the rules for an ocean that has waited untouched since the solar system was young. That first confirmed contact could lock in decades of advantage, scientific prestige, technological patents, diplomatic leverage, and narrative control over humanity's expansion into the outer solar system. What if the moment we've dreamed of for centuries, proof of life beyond Earth, arrives not through careful international consensus, but through a single nation's bold, unilateral move? That possibility is no longer science fiction, it's on the current trajectory. Here, we reach the moment that could define the rest of the century, the tipping point where scientific curiosity collides head-on with national ambition, resource strategy, and the fragile norms that have governed space exploration since the 1960s. Let's be very clear about the most plausible near-future scenario. Suppose, sometime in the late 2030s or early 2040s, a Chinese spacecraft, perhaps launched on the next-generation Long March 9 heavy-lift rocket, successfully deploys a lander on Europa's fractured ice plains. The lander carries a cryobot, a nuclear or radioisotope-heated melt probe designed to descend slowly through the ice shell over months or years, melting a clean path while sterilizing itself to the extent possible under planetary protection guidelines. Eventually, the probe reaches the ocean interface, releases a small submersible or simply opens sampling ports, and begins transmitting chemical data, microscopic images, and perhaps the first unambiguous biosignatures ever detected beyond Earth. The instant that data packet reaches mission control in Beijing, encrypted, analyzed, and then selectively shared with the world, everything changes. If the findings show only intriguing prebiotic chemistry, China gains unmatched prestige as the first to directly sample an extraterrestrial ocean. They would control the narrative around habitability in the outer solar system for years. If the data reveal microbial life, even something as simple as vent-dwelling prokaryotes, the discovery becomes the single most profound event in human history since we first looked through a telescope. China would be the nation that delivered that proof, giving them unparalleled leverage in every international forum, from the United Nations Committee on the Peaceful Uses of Outer Space to future treaties on extraterrestrial resource utilization. From a strategic standpoint, the advantages compound quickly. Access to Europa's water means in situ production of propellant for missions to Callisto, Ganymede, or even Saturn's moons, turning Jupiter into a forward operating base rather than a distant waypoint. Hydrothermal vent chemistry could yield patents on novel catalysts, enzymes, or radiation-resistant materials that feed back into China's domestic tech ecosystem. And perhaps most critically, the precedent of unilateral landing and sampling would normalize a first-mover takes the lead approach to subsurface oceans, weakening the consensus-based model that has dominated planetary protection and space law since Apollo. Other nations would face intense pressure to either partner on China's terms, accelerate their own aggressive programs, or accept a secondary role in what suddenly becomes the most valuable real estate in the solar system. Of course, none of this happens in a vacuum. The Outer Space Treaty prohibits national appropriation of celestial bodies, but it is silent on subsurface resources or private public exploitation of alien water and biology. China could argue, as they already do with lunar regolith and deep-sea nodules, that use does not equal ownership, especially if the activity is framed as scientific research with peaceful intent. Meanwhile, the United States and Europe would likely push for urgent new protocols, emergency sessions at COSPAR, and perhaps even sanctions or diplomatic isolation. But by then, the hardware would already be on the ice, the probe already melting downward, and the data already flowing. This is the tipping point we are approaching. Not a dramatic military standoff, but a quiet, irreversible shift in who writes the rules for humanity's expansion into the outer planets. The first confirmed touch of Europa's ocean could lock in advantages that last decades: scientific, economic, technological, and narrative. What if the moment we prove we are not alone arrives not as a shared triumph of humankind, but as a national achievement claimed by one flag? That single question now hangs over every budget debate, every launch manifest, and every quiet prototype test in labs from Pasadena to Shanghai. Now we arrive at the crossroads, the point where speculation meets decision, where the path we choose in the next decade could determine whether Europa's hidden ocean becomes a beacon of collective human wonder or another chapter in the long story of competition over shared frontiers. The good news is that we are not yet locked into a zero-sum race. There is still time to steer toward cooperation, and history offers a powerful precedent: the International Space Station. What began as rival Cold War programs, Apollo-Soyuz, then Mir and shuttle docking, evolved into the most complex engineering project ever built by multiple nations, a floating laboratory where Americans, Russians, Europeans, Japanese, and Canadians have worked side by side for over 25 years, despite geopolitical storms on Earth. That model proved that even bitter competitors can share infrastructure, data, and risk when the goal is bigger than any one flag. Applying the same logic to Europa would mean treating the subsurface ocean as a global commons from the start. An international Europa exploration framework, perhaps under the auspices of COSPAR or a new UN-led body, could set binding rules for planetary protection, data sharing, sample return protocols, and non-appropriation of biological or chemical resources. Missions could be modular. NASA's Clipper provides the orbital reconnaissance and plume sampling. China contributes a lander and cryobot technology proven in Antarctic analogs. Europe supplies advanced spectrometers and radiation-hardened robotics, while private players like SpaceX or Blue Origin handle heavy-lift logistics under strict oversight. The first direct samples could be divided and analyzed in joint labs, with raw data made public in real time, so no single nation controls the narrative or the patents that might flow from extremophile biochemistry. The benefits of this approach are enormous and mutual. Shared risk reduces the financial burden on any one country. Drilling through kilometers of ice under Jupiter's radiation belts is not cheap. Pooled expertise accelerates progress. American remote sensing experience combined with Chinese drilling know-how could get us to the ocean floor years sooner than any solo effort. And most importantly, it preserves the moral high ground. If we discover life, even microbial, the world would see humanity rising together to meet one of its oldest questions, rather than squabbling over who gets to name the first alien microbe or patent its enzymes. That shared triumph would inspire generations, much like the moon landing did, and it would strengthen the fragile norms of space law before they are tested by real exploitation. Yet the window for this cooperative path is narrowing fast. Every year that budgets stagnate in the West, while launch cadences accelerate in China, the incentive for unilateral action grows. If a Chinese mission reaches the ice first and begins melting downward without broad international buy-in, the pressure to respond in kind or to accept secondary status will become overwhelming. The Outer Space Treaty's principles are only as strong as the political will behind them. Once boots or treads are on the ground and data is flowing, retroactive rules become much harder to enforce. So, the choice is ours, right now. We can double down on suspicion and national silos, turning Europa into the next contested domain, or we can remember that some discoveries are too big for any one nation to own. An international Europa consortium isn't utopia, it's pragmatism, grounded in precedent and self-interest. The question is whether leaders on all sides have the vision to choose it before the first cryobot touches alien water. Because if we wait until that moment to start talking cooperation, the conversation may already be over. We've descended through the ice, touched the midnight ocean, reached the vents on the seafloor, and surfaced again to face the very real race unfolding right now among nations that see Europa not only as a place of wonder, but as the next great arena for human ambition. What began as a journey into the unknown has become something far more immediate, a mirror held up to ourselves, reflecting how we choose to approach the last truly untouched frontiers of our solar system. The hidden ocean beneath Europa's crust is more than water and chemistry. It is a test of whether humanity can extend the best parts of our story, cooperation, curiosity, stewardship, into the cosmos, or whether we will repeat the oldest patterns of competition, exclusion, and short-term gain. If we allow this to become a unilateral sprint, one nation planting its hardware first, claiming first samples, setting first precedents, the consequences ripple far beyond Jupiter. It would accelerate a fragmented, militarized approach to space resource utilization, where every new discovery becomes another point of leverage rather than shared knowledge. Planetary protection could erode under the pressure of national security or technological superiority arguments. Future missions to Enceladus, Titan, or even subsurface oceans on exoplanets would start not with international protocols, but with suspicion and countermeasures. And perhaps most painfully, the moment we prove life exists beyond Earth might arrive not as a unifying "we are not alone" revelation, but as a proprietary data drop guarded by one government's firewalls, a discovery that divides rather than elevates. Yet the alternative is still within reach, and it is not naive idealism, it is calculated realism. The International Space Station showed that sustained cooperation is possible even when trust is low on the ground. A similar framework for Europa, joint science working groups, shared mission architectures, open data pipelines, mutually agreed planetary protection standards would spread the enormous costs, multiply the expertise, and preserve the moral authority that comes from acting as stewards rather than claimants. It would ensure that if, or when, we find microbial life, the news belongs to every child on Earth, not just to the citizens of one country. And it would set a precedent that could guide us through the even harder choices waiting on worlds with thicker biospheres or clearer signs of complexity. The clock is ticking. NASA's Clipper is en route, gathering the reconnaissance we desperately need. China's roadmap points toward direct access in the coming decades. Private companies are already eyeing icy moon logistics. The decisions made in the next 5 to 10 years, funding levels, treaty negotiations, partnership offers, red lines drawn or erased, will lock in the trajectory. We don't have to choose between wonder and wisdom. We can have both, but only if we act deliberately before the first cryobot melts through that final kilometer of ice. Europa's ocean has waited billions of years in silence. When we finally reach it, let the first words transmitted back be ones of shared awe, not guarded triumph. Let the discovery remind us that some things are too vast, too ancient, and too profound to belong to any one nation alone. Thank you for diving this deep with me. If this journey through hidden waters and human choices moved you, hit that like button, subscribe to the channel, and turn on notifications, because the solar system still has many more secrets waiting to be told. Until the next frontier, keep looking up and keep asking, what if? The end, for now.